Hello everyone, in today's video we're going to be looking at the reactivity of benzene compared to the reactivity of an alkene. Now in order to do this first we're just going to cover the structure of benzene and that delocalized system. So if we just remind ourselves, when we're looking at the structure of benzene, we have all of our carbons in a six-membered ring, and the carbons and the hydrogens are all in the same plane. We also have p orbitals that are 90 degrees to the plane of the atoms, and each p orbital has one electron. Okay, like that. And then the adjacent p orbitals will overlap to form a pi system. So these are the ones at the top overlapping, these are the ones at the bottom overlapping, and that forms that pi system above and below the plane of the atoms. Okay, so we have in this system, we have 6 electrons, and because they are free to move around anywhere in that pi system above and below, we say that those electrons are delocalized. So that's our structure of benzene. We've got that delocalized system, and that gives rise to this drawing that we use, that model that we use for benzene. Okay, so we've got 6 delocalized electrons that are free to move over those 6 carbons found in that ring. Let's now have a look at an alkene. So I'm just going to go for the simplest alkene. We'll just go for ethene. And again, let's just remind ourselves of the bonding in ethene. So we've got our carbons and our hydrogens all in the same plane in ethene. We've got our sigma bonds drawn as solid lines over here. We then have a p orbital on this carbon, again 90 degrees to the plane of the atoms, and a p orbital on this atom, this carbon atom over here, again 90 degrees to the plane of the atoms. Again, each p orbital is holding one electron. Those p orbitals then overlap like that, and that's going to form a pi bond above and below the plane of the atoms. Okay, and in this pi bond we have 2 electrons between these 2 carbon atoms. Okay, so these 2 electrons can only be found between these 2 atoms, and therefore we say that those 2 electrons, they're not delocalized, we say they are localized, so they can only be found between those 2 atoms. Okay, so those 2 electrons are what we class as being localized. Okay, so that's the structure of benzene and alkenes covered. Let's now compare their reactivity. So one of the reactions that we've looked at for both alkenes and for benzene is the halogenation reaction. Okay, so we're going to look at what happens when we have an alkene with a halogen. So I'm just choosing bromine for this example, and then we're going to look at what happens when we have benzene with bromine. Okay, so in the alkene that we just covered, I've just got cyclohexene over here. In that alkene that we've just covered, we have 2 localized electrons in that pi bond there. Okay, because of this, because they're localized, we say that this alkene is very rich in electron density. It's a high electron density, and because there's a high electron density across this bromine molecule over here, it can induce a dipole. Okay, so as we've seen, we induce a dipole across here, pushes the electrons in this bromine-bromine bond slightly closer to this bromine over here, and now we have formed so this bromine over here is our electrophile now. Okay, it's electrophilic enough to have a reaction between this double bond and that bromine electrophile. So we see this occurring over here. Okay, and then as we know, the reaction continues. You form your carbocation, and that leads us to our final product over here. Okay, and as we know, this is electrophilic addition that this undergoes. Okay, so in this case, for any alkene, alkenes have enough electron density, they are electron rich enough to be able to induce a dipole on the electrophile that they're reacting with. Okay, and therefore this reaction over here does not require a catalyst, it doesn't require to be heated up. This, in fact, the one that I've done over here is the test that we use for alkenes. We just add bromine water, and the bromine will react with the double bond and therefore decolorize bromine water. Okay, so that's with an alkene. Alkenes are very reactive with our halogens because they can induce a dipole across the halogen-halogen bond. Now let's have a look at benzene. So again, in this reaction, we've got a halogen, we've got a bromine in this case, a bromine molecule in this case, and we've got our benzene. Now, if you remember, in this reaction, we usually require catalyst, okay? Because the reason for that is when we have our benzene molecule, because we have 6 electrons that are delocalized, we can see that this molecule over here isn't electron rich enough. Because those electrons are constantly moving around, they're delocalized. At no point in this molecule is one side of it going to be electron rich enough to induce a dipole across our bromine. Okay, so our benzene molecule is not electron rich enough to induce a dipole across the bromine-bromine bond, and because of that we need to have a halogen carrier which carries out this step for us. So if I just go for FeBr3 and then that Br molecule, that bromine molecule there, that then forms this species for us. Okay, and this is electrophilic enough to react with that. Okay, so rather than benzene reacting with that bromine molecule where it can't induce a dipole, now in the first step of the mechanism, using the halogen carrier, we produce this bromonium ion. And that bromonium ion has a positive charge. So if I now change this over here, because it has a positive charge, it is electrophilic enough. The benzene does not need to induce a dipole across anything, and therefore the electron, 2 electrons from our delocalized ring can then easily go to our electrophile. Okay, so over here we need to produce a bromonium ion which is electrophilic enough to react with our benzene ring. Okay, so you do need to be aware of the difference in reactivity of benzene compared to alkenes. Benzene is not electron rich enough to induce a dipole across the bromine molecule, and therefore it requires a halogen carrier, whereas alkenes are electron rich enough, they have localized electrons, and therefore they can induce dipoles across bonds.